Welcome. So, in this lecture we are going to talk about sampling methods under constant on off time digital modulation. So, here we will first recapitulate our analog constant off time current mode control, then we want to present mixed signal current mode control, that means the digital architecture of constant off time current mode control. Then what are the difficulties using uniform sampling, then what is the logic behind mixed signal constant on time current mode control, and then event based sampling in constant on off time control. So, if we recap our peak current mode like constant off time control, and we have learned in our previous course in NPTEL course where it is analogous to trailing edge peak current mode control, but the only difference here the off time is constant. In regular current mode control our time period is constant, here the off time is constant, but otherwise it is equivalent like in the peak current, I mean it controls the peak current. And that means if you take this peak current reference, this is my peak current reference. So, it is here and it is compared with the sense inductor current, and the output of the comparator goes to a edge detection circuit, and then it enable the monoshot timer, and this timing parameter is nothing but our off time. So, our off time is loaded here, and as long as this is off, then output of the monoshot timer will be high and it will simply turn off the switch. And how does the mixed signal off time peak current mode control look like? So, in this architecture we are considering the same method, that means analog current loop, that means it is the peak current reference analog loop and it is compared directly with the sense inductor current, and you can see this logic remains same, and also that this logic, the monoshot timer logic, that means this is our constant off time logic, constant off time modulation. This is a constant off time modulator. This remains exactly the same what we have done in the analog current mode control, and here reference current is also in analog and inductor current is in analog domain. So, it is an analog comparator. So, these are all in analog domain, but only difference in this part. If you look at this part, in the analog version actually there is no digital loop, that means here since we want to digitize, so here we need to use an A to D converter, and then this is a digital compensator, and then there is a D to A converter, and that is why it is called mixed signal, because your current is in analog domain and the voltage loop is in digital domain. And this has been discussed in detail in this paper. What is the benefit? Because if we talk about the benefit for keeping the voltage loop in the digital domain, in fact in this paper also it is discussed, the same structure, one comparator, one DAC, one ADC, you can in fact reconfigure to constant on time control by suitably. Actually for constant off time you need to consider the minimum on time, that we also discussed earlier, and monoshot timer actually is configured as a constant off time modulator. If you change to constant on time, then this will be minimum off time and this will be constant on time modulator, that is it. And then based on this edge detection circuit you need to change this algorithm. So, in this form right now it is by default set as constant off time, but you can configure to constant on time by switch, because this whole logic is in digital domain. So, this is in digital domain. So, you can actually make this logic, you can just little bit modify this logic and it will work, and everything else remains same, like a voltage loop in digital and then current loop analog, number of ADC, DAC, everything remains same. But we will also discuss there will be a change in the sampling clock. That means if we talk about the sampling clock, what should be the edges of sampling clock, that will be different for under constant on time and off time. So, this architecture is quite similar, the analog part similar to analog current mode control, but digital part is added, and this digital part we can actually program. As I told, it is not necessary that you have to use always the compensator output as the reference current. We can program, that means we can keep a programmable current limit, we can adjust, we can do a trajectory tracking kind of control. So, we can do a very fast recovery control using this modulator. Now, this constant off time modulation, we are using uniform sampling if we use, because as I said, we need to discuss about this sampling clock. So, what should be this sampling clock? Because this is a variable frequency modulator. This is a variable frequency modulator where any small change in disturbance in the initial condition or even the sensing noise, it can affect even cycle by cycle little bit. There can be a jitter in the switching clock because it is actually only the off time is constant here, but the on time actually comes from the comparator output. So, if there is any sensing noise and if the noise varies cycle by cycle, then you may have some jitter in the on time, and as a result there can be a slight jitter in the switching clock. So, that means you cannot guarantee exactly in a real system that on time will be exactly identical. Now, the question is that if time period is not exactly identical and we can think of a random number that can be a slight variation of the switching frequency for a range within a small range, then how to sample? If you use a uniform sampling here, I am showing. Suppose you use a uniform sampling clock which is a fixed frequency, and you set this sampling clock in such a way that you need to achieve some desired switching frequency. That means you want to achieve a desired time period by suitably setting this off time, and you set this sampling clock. What will happen? Suppose if you sample right here and if you update, because the sample current voltage will come through this error voltage and compensator, then it will pass through the DAC. So, that means the output of this DAC. So, this is my output of DAC. So, we are assuming that output of the DAC is updated immediately, but practically it is not possible. In that case, it may so happen the sampling point and the switching point can vary, because in fact we have discussed at the very beginning of this week lecture, when we discussed lecture number 11, the basic sampling mechanism in variable frequency and fixed frequency modulation. So, there will be a difference. So, here if we use this, but it is an infeasible sampling because you cannot update the reference current immediately at the sampling point, because there will be a conversion time and computational time. As a result, your practical waveform will look like this. That means, this is your sampling point where you are sending the sampling comment, and we have discussed that if this is your ADC and if you are sensing this output voltage and this is your sample output voltage, I can say V0n. So, this you require a sampling clock. Okay. So, you require a sampling clock here. So, this sampling clock if you use fixed, and here we are providing a delay for accommodating the conversion and computational time. But even with this, it is practically feasible, we can implement. But you will see, because when you go to MATLAB simulation in the next week lecture, we will see this will lead to multi-limit cycle oscillation, because there will be a mismatch between the sampling point and the switching point, because we are using a fixed frequency sampling clock. So, that means the sampling point is fixed in every cycle, but the switching time period can slightly vary, and as a result you may end up with mismatch, and that will lead to multi-limit cycle oscillation. So, that means the problem is that you can have mismatch between between sampling point and switching point. And this is basically asynchronous. They are asynchronous. They are not sync, asynchronous. And that will lead to what is known as multiple limit cycle oscillation. Multiple limit cycle oscillation. And we will see in the subsequent lecture when you go to MATLAB simulation. Okay. So, multiple limit cycle oscillation. So, that means that is one of the drawbacks. But if you increase this sampling rate, you may reduce this effect mismatch, but still you may not totally eliminate this problem. But the problem will be if you use a very high sampling rate, then your ADC power consumption will increase and your computation, because you need to update this reference current much frequently. So your the computational requirement or the power consumption will increase. So as a result, it may incur more losses. So in order to overcome that, we can use, instead of uniform sampling, we can use a event based sampling. How do we do that? So you take an event, for example here, since it is a constant off time control, so constant off time means it will enable a monoshot timer, and for this particular duration your monoshot timer will set at the active high, because that is the monoshot timer, it is the unstable state. So it will remain high for that particular duration, then it will come back to a 0 state. So when the monoshot timer is about to finish the counting, that means when it just finished the counting, that means this age, we can actually take a sample. Okay, that means it is with respect to an event. And what is the event? Whenever the monoshot timer finish is counting, then we will actually sample the output voltage. So that means first thing, the conceptually, that means that sampling point is the first logic. Sampling point linked with monoshot timer activity. Why I am saying activity? Here I am taking the sample when the monoshot timer finishes its counting. I can also select the sampling point when the monoshot timer is just enabled, or I can select the sampling point in between anywhere in the monoshot timer. So that means we are linking this sampling point with the activity of the monoshot timer. So that means it is an event. So we are not talking about any fixed frequency clock, and whenever the monoshot timer is activated, then we have the freedom to select the point anywhere between the timer. Now you can ask me, what will happen if you sample right at this point? So if you sample right at this point, then the problem is you may end up with noise, because this can be a noisy point. Okay, so you have to be careful that, because whenever the switch will turn on, there can be a spike, switching spike. So you need to avoid. One way to avoid, whenever you identify the monoshot timer finishes its counting, this is your Q pulse. That means I am saying the Q pulse is the gate, it is the controllable gate signal, controllable pulse. And when this Q signal goes to the gate drive, there will be a gate drive, right? Gate drive. Then the gate drive will actually generate the high pulse and the low pulse for the respective synchronous switches, because we have two switches, right? One switch is here and other switch is here. If you take a buck converter, so this, let us say it is the high pulse and it is the low pulse. And if you are talking about a practical switch, there will be a finite turn on turn off time, and in order to avoid any shoot through, then we need to provide some delay, or basically dead time, and also the driver will also have some propagation delay. So as a result, the actual, that means if Q is here, the actual QL, that means if you take the actual QL, so actual QL can be, it can go high somewhere here, that means it can go high. So there can be some delay due to the driver, or there can be some delay due to avoid, that means due to the dead time. So as a result, even if you send the sampling command right at the, whenever the monoshot timer finishes is counting, this is good enough, because practically the switch cannot be turned on at this point, because there will be some delay. So as a result, we will be able to capture the clean sample. But the bottom line is this: we are linking the sampling point with respect to the activity of the timer. As a result, it is called event based sampling. And we have discussed in sufficient detail that what will be the impact on stability if we keep on changing the sampling point. That means if you take sample either here or here or here, based on that there will be various possibility, because one thing is a regulation. Suppose if you take the sample here, which may be at the end of the off cycle, then if you take the ESR dominated ripple. Suppose if you are talking about the output voltage ripple of a buck converter, if the output voltage ripple, let us say it is primarily dominated by the ESR of the capacitor, then the ESR ripple profile will be exactly identical to the inductor ripple profile in a synchronous buck converter. So as a result, if this is my inductor current, profile, then if I talk about the output voltage profile, then output voltage will also have a similar kind of profile here, and I am talking about this is the output voltage. So this is my reference, this is my average output voltage, this is my average value. So this will also have. Now if we take the sample right here, we are talking about the sample close to the valley point of the voltage, and if you regulate the voltage, what will happen? Your actual average output voltage will be slightly higher than Vref. So that may lead to some kind of penalty in the regulation. So to avoid that, you may choose the sampling point at the midpoint, so that you can actually sample somewhat close and you can achieve better regulation. So all these possibilities exist in this tech, and we have discussed some of detail in this paper. So the bottom line is that here we are talking about event based sampling. Now, so earlier event based sampling, there is a delay, because while we take the sample at this point, but actually we are updating the reference current somewhat later, and this is to accommodate our ADC conversion as well as controller computation time. So as a result, this will provide some headroom for this conversion. So it is practical converter. But suppose if you use a software control architecture, or if you are using a slower A to D converter with a slower conversion time, you may take a full cycle delay. That means you take the sample, you can take sample again at this point, there is no issue, and you can update next cycle, or you can take the sample just where before the switch turns on, because you are actually trying to sync the activity with the timer, monoshot timer. When the monoshot timer is enabled, then you can take the sample, and then you can take the action in the next cycle. So this is something like a one cycle delay. So this may actually potentially provide more headroom for I would say the conversion and computational time. But we will discuss when we will go for analysis, at least one case study will show what is the effect of sampling delay in the stability. So you will find, because there will be cycle by cycle stability we have to ensure. That means we do not want any subharmonic instability. So to avoid any subharmonic instability, we need to find out some gain, controller gain, proportional and integral gain, and this gain, range of this gain will depends on the sampling delay. So if you take a larger delay, you may end up with a smaller range of controller gain for stable behavior. So it will actually give rise to a conservative choice set of controller gain. So that will be the penalty that we will discuss. So that means we may, if we incorporate delay, first of all it will penalize, because this delay will be introduced in your loop. So it will naturally slow down the transient performance because of this whole cycle delay. But as I said, digital control has other provision, alternative path to speed up the transient. But in effect at steady state, this delay, if we increase the gain, it may also end up with subharmonic oscillation. So some part we will discuss in the stability analysis aspect, but not too much, because this course we do not want to make too much advanced. We should know the basic concept first. Now if we are going for mixed signal constant on time control, and we know this control is analogous, it is analogous to valley current mode control, valley current mode control, where we are directly controlling the valley current, and the reference current will be the value of the inductor current. So when the inductor current hit the lower limit, so we are going to the waveform. So it is exactly analogous to valley current mode control in fixed frequency, and the difference here, in valley current mode control for fixed frequency operation, we keep the time period fixed, but here we are keeping the on time fixed. But you see everything else is same. That means what is the change here? Only this timer value is updated with the minimum of time. If you go back to the previous diagram, if you see, what is the change? Maybe this terminal even you do not have to change, because you can accordingly take care in this block diagram. So here you see there is a monoshot timer, there is a on time, and the age, whether it is a positive age or negative age, that you can always change inside the digital block. It's not a big deal. And the date time also we will have, because when you learn HDL coding, we will actually synthesize this whole thing in a Verilog code. Okay. But here the difference is, you can see the comparator, again analog comparator. So you may not need to change the polarity of the terminal, or that means you do not need to physically change the terminal of the comparator. You can keep it as it is, but you have to take care that action in this digital block. So here again you need a constant of time, minimum of time block, that is a small timer, and another monoshot timer. So all these blocks are common, only some functionality of these digital blocks will be different, and that can be taken care just inside the digital block without fundamentally changing anything. So here it is analogous to valley current mode control. How does it look like? You know, valley current mode control means, generally we know whenever in fixed frequency the clock edge come, we turn off the switch, and when this actually the inductor hit the lower limit, then the switch is again turned on. So in fixed frequency it is linked with the clock, but here there is no fixed frequency clock because it is a constant on time. So how does it work? So first, if the monoshot timer is enabled, so it is enabled for this T on duration. Once it is disabled, then the switch is turned off, and when the switch is turned off, the inductor current start falling, and when the inductor current hit the lower limit, that is my valley reference, then again the switch turn on, or basically it will trigger the monoshot timer, and the monoshot timer goes high. So that is how this operation, and we have discussed in sufficient detail. But in the digital architecture, only the voltage loop is digital, everything else is analog. Here, how to sample? Again, if we use an uniform sampling, that we discuss. So what will happen? There will be a mismatch between the sampling point and the switching point, and it will again lead to multi-limit cycle oscillation, and we want to show MATLAB case study for this particular example also. So we have identified that constant on time modulation, even where uniform sampling may lead to multiple limit cycle oscillation. So then again, similar to constant of time, we can now do even based sampling. So how do you do that? So here it is a constant on time modulation, which is a variable frequency like a valley current mode control, where we need to identify, if you think there, whenever the monoshot timer finishes is counting, then the switch is turned off and inductor current start falling, and whenever the inductor current reaches the reference current, which is the valley current, then again the monoshot timer is activated and the switch is turned on, and it continue to remain on for the on time duration when the monoshot timer is activated. And we have discussed in the previous lecture under constant of time, that means here in event based means we want to link the sampling point with respect to the activity of the monoshot timer. So here we want to take the sample little bit earlier than the monoshot timer finishes counting, because we can choose any point in this duration, because this is a counter, right, and it will start counting, like if you take a just simple counter. So counter will be just simply start counting, and once it reaches, then it goes low. So this is, let's say this is your T on duration, right. So if we fix a comparator here, so that means you can create a clock, whenever it goes midway, then you can actually activate this clock. So this can be used as the sampling clock. So either midpoint or anywhere in this point, because it is ultimately a counter. Now if you send the sampling command here, then you can update the current difference after some time, and this is to accommodate the delay due to the ADC conversion as well as controller computation. Although in this diagram the delay seems to be very small, but you can always increase the delay amount, right, or even you can take a full cycle delay that we have discussed. So all these possibilities are there, and it is for the conceptual understanding that we need to introduce a delay to accommodate conversion as computational time, but it is an ultimately event based sampling. Okay. So in summary, we have recapitulated analog constant of time current mode control. We started with this, then we have discussed mixed signal constant of time current mode control, then we have understood what are the difficulties using uniform sampling, then we have also seen the constant on time current mode control, mixed signal architecture, and finally We have also discussed event based sampling in constant on off time control. So, we got some reasonable idea about the how does this kind of control logic operate. So, then we will discuss a little bit about the architecture aspect in the next lecture. So, we want to finish here today. Thank you very much.